Have you ever wondered why time seems to fly when you're having fun, but drags when you're bored? What if I told you time could actually slow down or speed up? Welcome to the enigma of time and space, a world where the rules are not as straightforward as you might think. This is the realm of relativity, a theory that challenges our everyday understanding of time and space. Now, you might be thinking, time and space are constants, right? A minute is always 60 seconds. A meter never changes in length. But imagine, if you will, a universe where time can stretch and squeeze, where space can expand and contract. Sounds like a science fiction novel, doesn't it? But this isn't the product of a creative mind's imagination. This is the reality of our universe as uncovered by one of the greatest minds of the 20th century, Albert Einstein. Einstein's theory of relativity proposes that the laws of physics are the same for all observers, no matter their speed or direction. Sounds simple enough, right? But the implications of this idea are anything but. According to relativity, time and space are interconnected in a four-dimensional fabric known as spacetime. And this spacetime is not flat and rigid, but can be warped and distorted by mass and energy. In essence, the more massive an object, the more it distorts the spacetime around it. This is what we experience as gravity. And as for time, well, it's not immune to this distortion. Depending on where you are and how fast you're moving, time can appear to slow down or speed up. This might sound like philosophical speculation, but it's not. It's a scientific theory that has been proven correct time and time again. From GPS satellites that have to account for the effects of relativity to keep accurate time, to the detection of gravitational waves from colliding black holes, evidence of relativity is all around us. Intrigued? Let's dive deeper into this fascinating theory. To understand the theory of relativity, we must first understand that it comprises two parts: special relativity and general relativity. Let's start with special relativity, which Albert Einstein introduced in 1905. This theory is all about the constancy of the speed of light. What does that mean? Simply put, it means that light always travels at the same speed, regardless of the observer's motion or the source of light. It's always about 186,000 miles per second. Another key principle of special relativity is that the laws of physics are the same for all observers. This might seem like a no-brainer, but it's actually quite profound. It means, for example, that if you're in a spaceship moving at a constant speed, you can't perform any experiment that will tell you whether you're moving or at rest. Now let's move on to general relativity, which Einstein presented 10 years after his special theory. With general relativity, Einstein turned our understanding of gravity on its head. Instead of viewing gravity as a force between two objects, as Newton did, Einstein suggested that gravity is a result of the curvature of spacetime caused by mass and energy. Imagine you're on a trampoline. If you place a heavy ball in the center, it'll create a dip, right? Now, if you roll a smaller ball towards the heavy one, it'll move in a curved path towards it. That's a bit like how general relativity describes gravity. The Earth, for example, is like that heavy ball curving spacetime around it, and we, on the surface, are like that smaller ball kept in place by that curve. These two parts together form a complete theory that revolutionized our understanding of the universe. It's fascinating stuff, isn't it? But hold on to your hats, because we're about to delve even deeper into the enigma of time and space. Stay tuned. One of the most mind-boggling predictions of special relativity is time dilation and length contraction. Let's dive right in. Imagine you're on a spaceship traveling close to the speed of light. You have a clock with you, ticking away the seconds. But to someone observing from Earth, your clock appears to be running slower than theirs. This is the phenomenon known as time dilation. It's not that your clock is faulty or that the observer has superhuman vision. It's just that time itself is behaving differently due to your high speed. It's as if time is a river flowing steadily for the stationary observer on Earth. But for you, on your near-light-speed spaceship, this river of time is flowing more slowly. The faster you travel, the slower your time river flows compared to the observers. Now let's talk about length contraction. Back to your speedy spaceship, but this time you're holding a meter stick. To you, inside the spaceship, the stick measures 1 meter, as it should. But the observer on Earth sees it differently. To them, your meter stick appears shorter. It's not an optical illusion or a trick of the light. This is length contraction at work. It's like you're holding a rubber band that, to you, remains its normal length. But to an observer watching as you whiz by at near light speed, this rubber band seems to contract, to shrink in length. The faster you go, the more it contracts in the observer's view. These two phenomena, time dilation and length contraction, are direct outcomes of the constancy of the speed of light. They are predictions of Einstein's special theory of relativity, and as strange as they may seem, they are part of the fabric of our universe. It might sound like science fiction, but these are real effects that have been experimentally confirmed. General relativity takes us even further, predicting the existence of black holes and the bending of light by gravity. By now, we've already explored the fascinating concepts of time and space, their interplay, and the strange phenomena that arise due to this. Now let's dive deeper into the world of general relativity, where things take a rather unusual turn. Imagine spacetime as a fabric. It's not a flat, static entity, but rather a dynamic and curved one. This curvature is caused by mass and energy. Picture a bowling ball placed on a trampoline. The weight of the ball causes the trampoline to sag, creating a curve. Similarly, mass and energy distort spacetime, producing a curvature. This is the concept of curved spacetime. But it's not just about how mass and energy tell spacetime to curve. It's also about how this curved spacetime instructs mass and energy to move. Let's take that trampoline analogy again. If you were to roll a marble along the trampoline, it would naturally move towards the bowling ball, not because of a mysterious force pulling it, but because of the curve the bowling ball created. In a similar fashion, objects move along the curves created by mass and energy in spacetime. This interplay between mass, energy, and spacetime leads us to one of the most intriguing predictions of general relativity, the existence of black holes. When a sufficient amount of mass or energy is concentrated in a small enough space, it can cause spacetime to curve so intensely that it forms a black hole. These are regions of spacetime from which nothing, not even light, can escape. These predictions were so strange that even Einstein himself had doubts about them. But today, we have strong evidence supporting these predictions. So buckle up as we continue our journey into the enigmatic world of relativity, where reality often surpasses the wildest stretches of our imagination. The theory of relativity is more than a century old, but its impact is still felt today. It's not just the foundation for modern physics, it's also a cornerstone of the technologies we use every day. Consider GPS technology, for instance. The satellites orbiting Earth aren't simply transmitting data, they're also compensating for the effects of relativity. Because they're moving at high speeds and farther from the Earth's gravity, time on these satellites actually ticks slightly faster than it does on the ground. Without relativity, your GPS could be off by miles, not just feet. Beyond practical applications, relativity has also sparked our imaginations. It's introduced the tantalizing, if not yet fully understood, possibility of time travel. While no one has built a working time machine just yet, the theory of relativity allows for the concept in a way that was unimaginable before Einstein. It's given us a framework to dream and to explore, to ask, what if? But perhaps one of the most profound impacts of relativity is how it's changed our philosophical and cultural understanding of time and space. It's challenged us to think of these not as fixed and absolute, but as intertwined and mutable. This has had profound implications for everything from art and literature to philosophy and theology. In the end, the legacy of the theory of relativity is not just about scientific breakthroughs or technological advancements. It's about a fundamental shift in how we perceive our world and our place within it. It's about embracing the strange, the counterintuitive, and the mysterious. It's about the thrill of discovery and the pursuit of knowledge. The theory of relativity has forever changed our understanding of the universe, and its mysteries continue to captivate us. So the next time you feel time flying or dragging, remember, it's all relative.